Saturn is a very popular planet for one to visualize when they think of space, and the reason for that often is because it has very apparent rings, which are very evident in the photographs taken of Saturn. Now, what is the reason for these rings? We can attribute it to the Roche limit. So what is it exactly? We can define the Roche limit as the point at which a satellite is pulled apart by the gravitational force of the planet it is orbiting. So if we take the case of Saturn, Saturn can't have moons inside Saturn's rings because the Roche limit is the outer edge of the rings, thus meaning that everything on the inner edge of the rings has been broken up into little pieces because of the gravitational force. Another example is when the Shoemaker-Levy comet came close to Jupiter in 1994, but it got broken into little pieces which entered Jupiter separately. Now, it's hard to fully visualize what a satellite and a planet relationship actually looks like, so there are equations in order to quantify it. So we can set the distance between the two centers of the two objects equal to approximately 1.26 times the radius of the larger object times the density of the larger object over the density of the smaller object. And we set this all to the power of 1/3. And that's the equation for a rigid satellite. And fluid is a little different. We have distance is equal to approximately 2.44 times the radius of our larger object, and we're again multiplying this by rho large m and then over rho small m, and we set this equal to the power of 1/3. So we can see that the constants that we are multiplying our equations by, 1.26 for the rigid satellite and 2.44 for the fluid satellite, those are different, with the fluid's value being twice as large, and this means that the fluid satellite is twice as far away as the rigid satellite when compared to the Roche limit, because it is less able to support itself against a strong gravitational force where it would just break apart. So let's define our variables. We have rho large m, and then we can equate this to the density of the larger object, and then we have rho small m, and this is equal to the density of the smaller object, and then large r, which is the radius of the larger object, and then finally distance between the two centers of the two objects. So in order to truly understand the Roche limit and how it works, we have to look at our satellite closely by drawing the forces that are actually acting on it. So there is a outside force that is pointing away from the larger object that the satellite is orbiting, and this is Fg, or the gravitational force from the smaller object. So this is the force that keeps the object together and keeps it condensed and keeps it from breaking apart. While on the other side, we see the tidal force that the satellite experiences, called Ft, which is not to be confused with tension, is the tidal force, and this is applied by the gravitational force of the larger object that the satellite is orbiting. So there are predetermined equations for both of these forces. We can set Ft equal to 2 times the gravitational constant times the mass of the larger object times u, which is the mass of the smaller object, times r, which is the radius of the smaller object, and we set this all equal to d to the power of 3, which is distance being the distance between the centers of both objects. And likewise, the force of gravity also has an equation according to Newtonian gravity. Fg is equal to the gravitational constant times the mass of the larger object times the mass of the smaller object over the radius squared of the smaller object again. And just to provide clarification, the gravitational constant is g equals 6.67 times 10 to the negative 11th, so it's a very small number. So it's important to remember that at the Roche limit, the tidal force is equivalent to the gravitational force that the satellite experiences, because a little too much of the tidal force would mean that the satellite would be sucked into the larger object and would thus break apart because it can't withstand itself, while a slightly larger gravitational force would mean that the satellite remains condensed and in its spherical shape. So we can rewrite this formula by setting our two predetermined formulas equal to each other. So this is our equation, and this is important because we can directly derive those equations that I stated before, the one for the rigid satellite and the distance for the fluid satellite, and we can directly derive those from this relationship. So how we do that is, what variable are we trying to find? We're attempting to find d. So we set this relationship equal to d, and the result is r times the cube root of 2 mass of the larger object over the mass of the smaller object, or you could also write it as small m instead of u, and this is equal to distance. So we're on the right track to deriving our previous equations, but again, we're missing a very important variable, which is density. And how we solve, or how we include density in this equation, is by setting our two masses equal to their respective fractions. So we can say that the mass of the primary, which is basically the mass of the larger object, we can say that's equal to 4 pi times the density of that mass times its radius, which is large r because it's the radius of the larger object, over 3. And we can also do this for the satellite, which is orbiting the primary, and we can set it equal to 4 pi times the density of the smaller mass times the radius of the larger mass cubed, all over 3. So when we add these fractions in place of m and u in our distance equation, we arrive with densities equal to radius times 2 times the density of the larger mass times the radius of the larger mass over the density of the smaller mass times r3, and then this is set to the power of 1/3. And we can further simplify this by realizing that in this relationship, r and large r are the same. So we can say distance is equal to r times 2 the density of the larger mass over the density of the smaller mass to the power of 1/3. And then taking into account the predetermined constants for the rigid mass, specifically 1.26, times our equation of large density over small density to the power of 1/3, we arrive with the Roche limit for the rigid satellite, and the same process can be applied for the fluid satellite. Now I want to reiterate a very fundamental part of understanding the Roche limit, and that's the relationships between the tidal force and the gravitational force. We know that inside the Roche limit, the tidal force, which is 2 gravitational constant, times our masses and the radius over the distance cubed, we know that is greater than our gravitational force inside the Roche limit. While outside the Roche limit, we know that this relationship exists, except the gravitational force is greater than the tidal force. If the tidal force is too strong, it will overcome gravity that is holding the satellite together, and that object will rip apart, which happens when something drifts inside a Roche limit, which is the reason why rings form, and why on the outsides of rings you can find moons, which are still condensed satellites. Thank you for watching, and hopefully you did learn why exactly Saturn has rings.